Just in time for another episode of Business Calculus. This is 10.3, Continuity. So for any polynomial or rational function with a non-zero denominator, because if you remember, a rational function is a polynomial over a polynomial, at x equals a particular value, that's all this c means, some value, the limit of f of x as x approaches c is just simply the function evaluated at c. So in other words, all this says is if I want to know the limit of this function at a particular value, x equals c, I just simply plug c into the function and that gives me the limit. Well, because polynomials and rational functions with non-zero denominators are continuous functions, so the function is continuous at c, and we like continuous functions because there's going to be a lot of tools that if the function's continuous, it's very easy to make interpretations and see what's going on with the data. So when you have data values, right? Somebody went out and said, you know, at this time, 5 seconds, that this distance fallen is 20 meters. And then they took another time and another time. This is not continuous, but we assume it by connecting the dots. Most graphs of natural phenomenon are continuous. However, a lot of them in business and economics you're going to see are going to have these piecewise function, these step, that they're going to have these discontinuities, so we need to be able to figure out what to do with these. A function is continuous at a point if the limit exists and if the value at that point exists and they're equal. So this is important because it's a way for you to tell, how can you tell if a function is continuous at a point? Find the limit, find the value of the function at that point, and if they're the same, then that means they're continuous. So a function is continuous on some open interval, okay, if it is continuous at each point on the interval, and of course if it's not continuous, we call it discontinuous. So let's look at some limits here, and then we'll look at continuity. So what is the limit as f of x approaches 3? Get me a little laser pointer here. So what I do is x, this is my x-axis. As I'm approaching 3, well, there's my 3. So what is this function doing as I'm getting really close to 3? Well, it looks like it's approaching 2, which is actually the value, which is the same as f of 3. So it would be continuous at x equals 3 because the value of the function equals the limit. And so certainly it would be continuous. What is the limit as f of x approaches 1? Well, hopefully you can see it does not exist because there's a jump there. If I'm looking at 1, there's an actual jump. How about if I'm approaching 2? Well, it looks like the limit is approaching 1, but the value of the function at x equals 2 is this value up here. There's a hole right here, so the value of the function doesn't exist in this case at that point because there's a hole there. So as you can see, because the limit, remember I said the limit could care less the value of the function. The only time we care if the limit and the value of the functions are the same is if we're talking about continuity, and thus this certainly would not be continuous. If we're approaching 4 from the left, remember that little minus sign, so here we're coming from the left, I can see the limit is getting really close to 1, but f of 4 is actually halfway here, 0.5, so certainly this would not be continuous. So by looking at the graph from this interval 0 to 4, you can see that if I'm looking at 0, I'm continuous. Okay, notice because the circle's colored in, basically. If I'm looking at 1, it's not continuous, and you could either say because of a jump. If I'm looking at 2, it's not continuous because of a jump. 3, the limit and the value of the functions were the same, so it is continuous. And then at 4, there's a jump, so these would be your not continuous points. So a function is continuous on an interval if and only if it is continuous at every point in the interval. So how about this function, f of x equals x plus 2? Is it continuous at x equals 2? Well, think about this. This is a line, right? It's linear. And if we took the limit and we see that the limit as x approaches 2 is actually equal to the value of the function, then it would be continuous. How about this function? Is it continuous at x equals 2? Well, you can see it's a rational function, and if I plug in 2, I'm going to end up with, in fact, the numerator being 0 and the denominator being 0. So as we can see, g of 2, the function is not defined at that value, so certainly if it's not defined at that value, then it's not going to be continuous. However, does the limit exist? Well, yeah, the limit exists because remember we said the limit could care less about the value of the function. What the limit cares about is as we're approaching that x value, what's the value of the function approaching? And so in this case, if I factored out, remember x squared minus 4 is the difference between squares? So I have my x minus 2, x plus 2. I can cancel x minus 2, and then now I can actually plug in as x approaches 2, and I can get the limit, but the limit does not equal the actual value. How about this function? So I have an absolute value of x over x. Well, certainly we can see we can't plug in 0, and also in this case the limit actually does not even exist because we have a left-hand limit and a right-hand limit, and they're not the same. So that last example showed that, well, we had something going on with a limit from the right and something going on from the left. Well, we can actually have one-side continuity where a function is continuous on the right at x equals c if as I'm approaching c from the right is the same as my value of the function, and of course the same thing for approaching from the left. A function is continuous on the closed interval. In other words, this means the endpoints can be continuous as well if it's on a closed interval, and also on the open interval is continuous. So let's look at this function y equals the square root of 4 minus x squared. Notice that if x equals negative 2, so I would do negative 2 squared, which would be a positive 4. Negative times a negative is a positive. And I'd get 4 minus 4, which would give me 0. And it's okay to take the square root of 0 because that's 0. If I let x equal 2, 2 squared is 4, 4 minus 4 is 0. So because these values actually exist, and you can tell that because they're colored in, right? Is this function is continuous at every point in its domain. That's the key, because remember, you can't take the square root of a negative number, so you can't say it's continuous, you know, at like negative 5 or at 5 or something. It's only continuous in its domain. Also notice it's continuous at x equals negative 2. That's right continuous because I'm coming from the right of negative 2. And then left continuous because I'm coming from the left at positive 2. If two functions are continuous on the same interval, then their sum, difference, product, and quotient are also continuous, which is kind of nice. But once again, except for values of x, that makes the denominator 0 when you're dealing with rational functions. A constant function is continuous for all x. Okay, so for example, y equals 7, f of x equals 7, it's continuous. For integer n greater than 0, f of x equals x to the n. In other words, like x to the first power, x to the second power, x to the third power. This would be continuous. A polynomial function is continuous for all x. A rational function is continuous, again, except those that make the denominator 0. If we have a radical, one of these roots, if it's an odd positive integer, like the cubed root, the fifth root, then it's continuous for all x. But if we have an even root, remember, because you can't, let's say this was a square root, you can't take the square root of a negative number, so these values have to be positive, and that's why you're seeing that it's only continuous on this interval from 0 to infinity. So let's look at something like this. Is this function a continuous function? I think so, because last time I checked, that's a polynomial, and we just said a polynomial is continuous for all x. Is this function continuous? Well, we said rational functions are continuous except for the values that make the denominator 0. So in this case, -2, if I plug in -2, the denominator is going to be 0, or if I plug in 3, the denominator is going to be 0. So it is continuous everywhere except those 2 points. Now, this notation you may not remember from algebra, but what this says is I'm coming from -infinity to -2. I put a parentheses because I cannot equal -2. This little u is a union sign. It just kind of puts them together. And then I jump to the other side of -2. I go to 3. Can't equal 3, parentheses, union, 3, and then all the way out to infinity. Is this function continuous? Well, the property said for an odd positive integer, 3, it's a cubed root, that certainly this would be continuous. So what we look at now is we look to see if what's under the root is continuous. And that's this wherever f of x is continuous. And x squared minus 4 is a polynomial, and it is continuous. Well, how about this one? Is this function continuous? Well, this is a square root, so we said that it's continuous basically everywhere until what gets under this root becomes negative. So if I said at 1 minus 2 is -1, well, that's not going to work, right? So what you do is you set x minus 2 greater than or equal to 0, meaning positive values, and that gives you your continuous interval. And my little hint here, what does n equal? When you have a square root, it's actually a little 2. We just don't write the root. Whenever you see a radical without a little number beside it, we just don't write it because it's implied that it's a square root. All right, so we have what are called sign charts, and this section talks about how you can use them for solving inequalities. You're going to see later we're actually going to use them for something else, but let's go over what they show in here. And they're nice because it's very easy to see what's going on with a function. So suppose f of x is continuous on this interval from 1 to 8, and suppose the value at x equals 2 of this function is 5. Is it possible for f of x to be negative for any x on this interval? Well, think about this. If f of x, which is my y, cannot equal 0, then there's no way that I could have crossed this axis. So it says f of 2 is 5. So in other words, if you have a negative value, such as this one I made up here, the only way, if this is continuous, I can go from that point, 2, 5, to that point there. Did you see what happened? I crossed that x-axis. This says you don't cross the x-axis. This says f of x never equals 0, meaning your y value, you're never on or crossing the x-axis. So thus f of x must be positive for all x on this interval. And of course you could say the same thing if we said we started out with our point was in the negative. There would be no way it could ever go positive. So these sign properties, sign meaning positive, negative, okay, that's what we mean by sign. If our function is continuous on an interval and f of x does not equal 0, which we just said means we never cross the x-axis, then on this interval, and our f of x is greater than 0 for all x on this interval, or it's either f of x is less than 0. Okay, well, what does all that mean? It's a whole bunch of mathy stuff, right? It basically says If you didn't cross the x-axis and you're above it, then you got all positive values. If you never cross the x-axis and you're below it, then you have all negative values, and that's all that means. A real number x is a partition for a function if the function is discontinuous at x or if f of x equals 0. So in other words, we can partition, we can use that x-axis. Again, f of x equals 0 means I'm on the x-axis. We can actually use that to partition our signs where we go from positive to negative. And so that's what we use a sign chart for, is for analyzing graphs of functions. We use them for solving inequalities. We use them where to find the 0 of the function, and we partition it. And then we get test values to see if we're above or below the x-axis. So how we construct one of these is we find all the numbers which are points of discontinuity, like where the denominator is 0. Points where the function is 0, where the numerator is 0, but the denominator is not. We plot these partition numbers on the number line, dividing the line into intervals, and then we select a test number in each interval and determine if our function is positive or negative in that interval. And then you complete your sign chart by showing the sign, positive, negative, on each interval. So as I mentioned earlier, in this section, they show you how to use a sign chart for solving an inequality. We're going to do some other stuff with it later, but this is a nice little activity. So we want to solve this inequality. So what I do is I use this left side here as my function, x plus 1 over x minus 2. And the first thing I want to do to set up my partition is where is x undefined? Or where is the function undefined? At what particular value of x? Well, it looks to me at x equals 2, right? Because that would make the denominator 0. Well, another partition, remember, is what value of x is the function equal to 0, meaning the top, the numerator. What would make the numerator 0? Well, it looks like -1, right? Because if -1 plus 1, that would give me 0. So I make my partition. At x equals -1, that's okay to plug in, so that's solid. I have an open circle for my partition at x equals 2 because the value of the function does not exist at x equals 2. It's undefined. Now what I do is these are my partitions. So in other words, I'm coming from -infinity. I hit -1. I go from -1 to 2. I go from 2 to infinity. The function is continuous, non-zero, and does not change signs within these intervals. So what we do is we pick values in these intervals. You can pick whatever number you want as long as they're in these intervals. And I plug them into my function and I see, do I get positive or negative values? So I decided here, why not plug in -2? Sounds good to me. I get a positive number. Here, I plug in 0 is always nice, right? Because that's easy to plug in. I get a negative value. And then finally over here, I plug in a 3, and that gives me a positive value. So constructing my sign chart says in this interval, all of these are positive until it hits 0, then it goes negative, then it becomes undefined, and then it goes positive again. Now just be careful with these two notations, my inequality notation versus my interval notation. The only big differences here is if you had a line under there like this, then you would actually have a closed bracket. So we've been talking about continuity. Let's see an application of this. First class postage is 40 cents for the first ounce and 14 cents for each additional ounce, up to a maximum weight of 3.5 ounces. We want to write a piecewise definition of the first class postage, P of x, for a letter weighing x ounces. Well, we go back up here and we read this, and it says 40 cents for the first ounce. So from 0, of course can't equal 0 because you ain't got a letter, right? So from 0 all the way up to the first ounce, so it can equal 1 ounce, so there's a line under it, would be 40 cents. Then we're going to add 14 cents for each additional ounce. So then we'll go from 1 to 2, 2 to 3, and this column here I'm just adding 14 each time. And then the last one would go from 3 to the maximum weight of 3.5. So we looked at this piecewise function, and how could we graph something like this? Well, each one of these are constants, right? Because 0.40 is just the function y equals 0.4. Then the next one, 0.54. Now notice these open circles because this left-hand side, it can't equal those. And so this is what the piecewise function would look like. And now we can ask some questions such as, is this function continuous at 2.5? Well, if you notice, because this is constant, and if I look where 2.5 is, I don't see a hole there, but again, constant functions are continuous. So since p of x is continuous from 2 to 3, not including 2, the open circle, and x is in that interval, then of course it would be continuous at 2.5. Well, let's check and see what the limit is as x approaches 3 from the left. So if I look at the up here, my definition, if I'm approaching 3 from the left, I'm somewhere in this interval from 2 to 3. And so it looks like I would be at that 0.68, which I can also verify by looking at the graph. Determine whether the function is continuous at x equals 3. Well, if I check my limit from the right side, I can see that I'm approaching 0.82, but if I check the limit from the left side, I'm approaching a different value at 3. So that's the only difference here, is my value that I'm approaching is different. So since the left-hand side does not equal the right-hand side, thus we do not have, it's not continuous at x equals 3.